In this video, we're going to solve a stoichiometry problem that asks us to go from grams of a compound to atoms of a particular element. So in this problem, we are given the mass of a particular compound. It gives us 5.28 grams of magnesium acetate. And what we're being asked to find is atoms of carbon specifically. Now, we don't have a direct conversion to go from mass of the compound into atoms of carbon, but what we do know is that in every 1 mole of carbon, we have 6.022 times 10 to the 23rd atoms of carbon. And that just comes from Avogadro's number, because a mole is equal to 6.022 times 10 to the 23. So we have that relationship, and we can use that as a conversion factor in our problem. So then the next question we have to ask ourselves is, okay, well, if we can go from moles of carbon to atoms of carbon, then the next natural way of solving that is to look for moles of carbon in that particular formula, and we can work our way backwards. So let's say hypothetically that we had 1 mole of magnesium acetate. We can figure out how many moles of carbon we have in the formula using the subscripts that are present in the formula. And keep in mind that whenever you have a subscript after parentheses, you're going to multiply all the subscripts in the parentheses by that one. So here what we're doing is multiplying the subscript of carbon by the 2 that comes after the parentheses, which really means that in 1 mole of this compound as a whole, we have 4 moles of carbon. Now that we know moles of carbon in that particular formula, we can go from moles of carbon to atoms of carbon. So we're working our way backwards to the piece of information that we do know, which is the mass of that particular compound. So now that we've established that relationship, we need to have some way of going from grams of that compound to moles of that compound so that we can eventually work our way to atoms of carbon. And the relationship between those two values, so something that can take us from grams to moles, is the molar mass of that compound, which means we need to calculate the molar mass of magnesium acetate. So molar mass of magnesium acetate will enable us to go from grams of the compound to moles of the compound. So in order to calculate the molar mass, we need the periodic table, and we're just going to identify all of the elements that are present in that chemical formula. Okay, so using the periodic table, 1 mole of magnesium has a mass of 24.305. 1 mole of carbon has a mass of 12.011. 1 mole of hydrogen has a mass of 1.01. And 1 mole of oxygen has a mass of 16.00 grams. Now, I do need to account for how much of each atom I have in the formula. And notice that we actually have 4 carbons in the formula, 2 times 2, which means I need to multiply that by 4. We have 1 magnesium, so we can leave the magnesium the way that it is. But we have 3 times 2, which gives us 6 hydrogens. So we need to multiply that mass by 6. And then we have 2 times 2, which gives us 4 oxygens in the formula. And then we're going to multiply all of that out and add everything together to get the total for the entire compound. So magnesium, I'm just going to copy exactly the way that it is because it doesn't need to be multiplied by anything. There's only 1 in the formula. So the carbon I multiplied by 4. Hydrogen we're multiplying by 6. And oxygen we are multiplying by 4. And finally, we can add all of these values together to get a total molar mass of the entire compound. Okay, and if I add all of that up, then 1 mole of magnesium acetate will have a mass of 142.41 grams. And we can use that relationship to connect the moles of the compound to grams of compound, because we're saying for every 1 mole of that compound, we have 142.41 grams. So I will go to the next page to give, actually I could delete the periodic table, I can solve it down here. That works. Okay, now that we have everything we need, I'm going to start with what is given to us, what we know. And we know the mass of the compound. So we have 5.28 grams of magnesium acetate. And I'm going to convert that to moles of compound first. And we're going to use the molar mass in order to be able to do that. So keep in mind that whatever unit is up top here, we have to put the same unit on the bottom in order for them to cancel so that we can get rid of stuff that we don't want. Which means that the relationship that takes me from grams to moles is the molar mass. And for every 1 mole of compound, we have 142.41 grams of compound. Well, I want grams of compound to be on the bottom of the equation so that the units cancel. Okay, I'm just going to abbreviate this as grams of compound. So there are 142.41 grams in 1 mole of compound. And now that we have that, the grams of compound cancel out. The next thing we have to do is go from moles of compound to moles of carbon. And we already established that from the formula subscripts. So that's telling us that in 1 mole of compound, we have 4 moles of carbon. And whatever unit is up top here, that's the same unit that we have to put on the bottom, which means that we're going to put 1 mole of compound in the denominator and 4 moles of carbon in the numerator. And now our moles of compound cancel out, and we're looking at moles of carbon. And finally, we want to go from moles of carbon to atoms of carbon, and Avogadro's number will take us in that direction. Now, I need to put whatever unit is up top here on the bottom, so moles of carbon will go in the denominator. And in 1 mole of carbon, we have 6.022 times 10 to the 23 atoms of carbon. And now we see that moles of carbon cancel out, and all we have to do is plug in the final values to get the number. So we're going to multiply everything up top and then divide by everything on the bottom. Now, just be careful when you're plugging Avogadro's number into your calculator, because you want to make sure you put this in parentheses so that you're not getting any strange exponent things going on. Okay, and I'm getting 8.93 times 10 to the 22 atoms of carbon, which makes sense because atoms are really, really tiny. If you are weighing enough of them to get 5.28 grams, and you can't even see an atom, they are so small, you should be getting a really huge number, because there's no way you can weigh an individual atom. You need a huge amount of them in order to be able to weigh them. So seeing something with a giant exponent means that we have likely gone